All right, so some of us have started to make the connection already, right, between what we were talking about before break and what we're about to talk about after the break, okay? So in particular, the title of this section maybe gives it away. We've got 3.2, the derivative as a function, okay? So if some of what we were doing at the end of class, end of before break class seemed familiar, you are spot on. It definitely has to do with the derivative. Okay, but I feel like a lot of times when we're learning about the derivative, you just kind of get a formula thrown at you, and we don't ever sort of talk about what it is or where it came from. So that's why I wanted to give us sort of a better feel for the story behind things. Okay, and so let's go ahead and pull up that. All right. Okay, so the derivative as a function, right? So what we know, we've taken a look at this average rate of change, which we affectionately abbreviate AROC. We've taken a look at the instantaneous rate of change, which we also abbreviate IROC. But if we also think about average rate of change as the secant, slope of the secant line, let me write that better. So it's average rate of change as the slope of the secant line, right? So the line between two separate points. And then the instantaneous rate of change, we would call the slope of, what was the name of that other line? Not the secant line, but the, that tangent line, right? So we've got the slope of a tangent line is our instantaneous rate of change. Okay, so slope of tangent line, right? So that's what we talked about before the break, and what's new in this section, and this will be the end of the content for exam 1, okay, which is not this Wednesday, but next Wednesday. What is new is something we're going to call the formal definition of a derivative, okay? So if you've taken calculus before, this probably will be very familiar to you. And if you've taken a course with me last semester, we did a little bit of this sort of at the end of the course. All right, so this formal definition, lots of words here, but it really summarizes what we talked about at the very end of that previous section, okay? So we can find the slope of the secant line, right? We call that the average rate of change, using this formula, f of b minus f of a over b minus a. And what you all as real mathematicians were like, but why can't we just use that? So when we pick cleverly 2 points and we call them x comma f of x and x plus h comma f of x plus h, with the stipulation that these are really close together, okay? We can use that to approximate the slope of the tangent line, which is our instantaneous rate of change. And we do that by taking that slope formula and just saying, let's make h really, really small, okay? Now it turns out that this limit, like this equation right here, shows up so many places in mathematics that we call it a derivative. We just give it a name. Or like anytime we want to find the slope between 2 points that are super, super close together, that's just called the derivative, okay? This equation in the blue is what we call the definition of the derivative. And I'm going to even put in front of this, this is the formal definition of the derivative, okay? We're going to see some new symbols. So this part on the right-hand side looks like what we had at the end of 3.1, right? But the new part for some of us is this side. Okay. The f with a little sort of apostrophe situation of x. So let's figure out what makes this the derivative, okay? So f prime of x is this f prime of x, and that is a symbol we use to say derivative. Okay. We can also say, for our brains, this is the same as the instantaneous rate of change. And the way that we say this is we say f prime of x. All right, so when we're reading it, we don't say f apostrophe x, we say f prime of x. All right. Now, some of us have asked me sort of outside of class, like what might be a good resource. All right, and I know that's one of the things that I want you to start to look at. There is a resource that you will find online where I've sort of cut a lot of these blue pictures from, okay? I hope you find that in your search for calculus resources, and I'll tell you folks next week what this resource is, all right? But just as kind of like a little mini scavenger hunt for you, if you can find where this resource is, I will tell you this is one of my favorite resources for calculus. And not just Calc 1, but also Calc 2, also Calc 3, okay? Some of us also mentioned talking about differentials, like differential equations. This resource is also super great for differential equations, okay? All right, so let's start with an example, okay? So in example 1, we're looking at the function f of x equals x squared. And part A says find the derivative using the formal definition of the derivative. What that means is I want us to use this to answer our question. Okay. How do I know? Because this is the formal definition, this is the formal definition, and I'm asking you to use the formal definition, okay? So the very first thing we're gonna do, we're gonna write down that formal definition, and then we're gonna do a bunch of algebra. I like how I say that, like that's like the most exciting thing you could do on a Monday morning. It's pretty exciting, but I know it's less exciting for some of us, all right? So we're gonna go ahead and write down that formula, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h, okay? Now, the first thing we're gonna do is instead of writing f of x, I want us to write x squared. Does that make sense? Like everywhere we see an f of x, we're going to replace it with x squared because that's our function in this particular question, okay? So f of x, we're going to say in this case is x squared. And so let me go ahead and write that out. The limit as h approaches 0 minus x squared. Okay.
May I ask a question?
Absolutely.
Just because my mind's curious again, can I distribute the f to the x, f plus to the h, and then you just cancel out the f of x's?
Ooh, okay. Not
Or
quite.
is that like, okay.
Not quite, but I'm so glad that you brought that up because I think that is one of the biggest questions about like, how do we, like, what do we do with this? Okay.
Right, okay.
Okay. So what does f of x plus h say? It says that everywhere in your function where you have an x, you're going to replace the whole thing with x plus h. Okay. And so this, if I think about this function that we have. This is really saying something squared. So if my input is x, I take x and I square it. But what if I said this? Let's take a little detour here, okay? What if I said f of 1? What would you folks tell me that is? What's f of 1? Like when I put in a x value of 1, what value do I get out? Great. Okay. How did we get 1? I know that sounds like a silly question, but humor me. How did we get 1? There we go. All right. So if everyone can see, Daniel has typed it in, Jordan's typed it in, Nora's typed it in. 1 squared will give us 1, right? So 1 squared gives us 1. So like, what did we do? Everywhere we saw an x, we replaced it with the value 1, okay? If I said f of 2, you would all say 2 squared, which gives you 4, right? If I tell you now, I want you to put in x plus h, you're going to have x plus h squared. So instead of 1 squared, instead of 2 squared, instead of x squared, now we have x plus h squared.
I have a question. Why did you square it?
That's a great question. Can someone maybe help answer that? Why are we squaring it?
Because that's the actual function. So fx is x squared. So you replace the x in the x squared with x plus h. So it would still be f plus h as if it was f the x. Then you just square it, if that makes sense.
Well, let me actually add a little page in here, okay? And I think this is important. It's a very, very important question. So I'm really glad we asked, okay? Let's say f of x equals x cubed, all right? If I translate this the way that Dallas has written, I'm saying f of some input equals that input cubed. If I had a different function, f of x equals x squared minus 2, that would be the same thing as saying whatever my input is, we do that input squared and then we subtract 2. Does that make sense, Alexis?
Yeah, so it's just that the problem was already squared, so you just squared the.
Exactly. That is exactly why. Okay.
Okay. And then if there was no squared or cubed in like the actual problem, then you wouldn't do it with the formula.
Yes, yes. So like if we had this, f of x equals sine x, that means f of my input means that I apply the sine function to my input. Okay. So this might be a more helpful way of thinking about it. Thanks for sharing that, Dallas. This might be a more helpful way of thinking about like what we do with that x plus h. Okay. So if we go back up here for a moment, right, our function is input squared. What is our input in the purple? X plus h. So I'm going to do x plus h squared. All right. Now this is so important. I do want to pause here for a moment and see how are we feeling with where this came from? Like just plugging in the f of x and plugging in our f of x plus h.
It feels pretty good to me. I just got a little bit confused because I thought we were just supposed to square the x in the x plus h, but now I get it.
Yeah, it is actually, and Dallas, it's so much, thank you so much for putting it that way, like in words, the input squared, that's what we're going for, okay? So we'll have plenty of chance to practice this again. And for right now, let's think, okay, so is this, I see a couple questions about like, why do we have the x plus h in parentheses? So I feel like maybe I used my parentheses kind of poorly here, all right? Does that make it, let me try one more thing. Does this make it more clear? Like in this case, the input is x plus h. In this case, the input is x. But in both cases, I'm squaring them because the function tells me to. Okay, great. Thank you. Okay. All right. So let's see what happens when we try and plug in 0 for h. Okay, so let's rewind to the very first day of class 2 weeks ago, where I said, you don't have a picture, just try substitution. Plug in the value and see what happens. Okay, so you tell me, you tell me what happens when we plug in 0 for h. What do we get in the numerator? What do we get in the denominator? All right, I see an undefined. Let's maybe go back a step to make sure we're all okay with why we get undefined. All right. In fact, what does the denominator become? 0 in the denominator, nice, which we know is already a problem, but what do we get in the numerator? Ooh, I see a couple good guesses, but I would say that's not entirely accurate. Ooh, okay. Daniel, how'd you get 0?
X squared minus x squared would be 0. So if you already have the 0 represented by the h, then it's not going to actually affect that equation. So yeah, so it just became x squared minus x squared.
Good. This x plus 0, when I square it, becomes x squared. And then x squared becomes x squared. And so I actually end up with 0 over 0. Okay. And so we know from last week that that's a problem for us. We have an undefined situation. Okay. So how do we handle this? Turns out we have to do sort of a similar feeling to what we did last week. We got to use some algebra to help us clean this up before we can actually get to our answer. Okay. And so let's sort of pick up right here. All right, so let's imagine we finished this. We tried this, we realized that didn't help us. Let's make things a little bit messier first. So we've got the limit as h approaches 0. Oof, that's a long fraction line. I'm going to keep the h on the bottom. But what do we get when we take x plus h and we square it? All right, so x plus h, that quantity squared. All right, I see one possibility in the chat, x squared plus 2xh plus h squared. I see a confirmation of that. All right. All right, this is a question for those of you who've had me before. What is x plus h squared not equal to? x plus h squared is not equal to this, okay? This is such a classic mistake. We actually sometimes call this the freshman's dream. Freshman, like it's your first year doing something, you're like, I sure hope that's true. Okay, it's not, unfortunately, because x plus h squared is actually x plus h times x plus h, and then we have to FOIL things, or we have to multiply those out and distribute, okay? So important. Let's put a little hot pink around this. So important. All right. So the purple part, the x plus h squared, becomes x squared plus 2xh plus h squared. All of this came from the x plus h squared. And then x squared just gives me x squared. All right. Go ahead and clean up that numerator for me. What do we get when we clean up that numerator?
Two xh plus h squared.
Yeah, those go to 0, right? So we get 2xh plus h squared. All right. Now, as we do these questions, a very common question that students have is like, how do I know if I'm on the right track? Maybe I didn't have a good algebra experience. So how am I supposed to know if I'm headed in the right direction? A very good clue is at some point, all terms should have an H, okay? That is a very good clue to look for. If you're like, I'm kind of following along, but I know I make a lot of algebra mistakes. At some point, pause and look. You should see that all terms have an H, okay? Why is that so important? Check this out. I'm going to factor an H out of the numerator. That's going to leave me with 2x plus h. And now this h and this h, well, they reduce to 1. Now I have this. Now let's plug in 0 for h. In a similar flavor as to the limit stuff we did last week, sometimes when we try substitution in the beginning, it gives us a problem, an issue, but then we do a little bit of algebra and we're able to sort of step around the problem and still answer the question. Okay.
So we're saying the function of 2x equals x squared.
Ah, that's a great question. What we're saying is that the derivative of x squared is 2x.
Okay, I see now.
Okay, so the derivative of x squared is 2x. And for some of us who've seen calculus before, they're like, well, I could have told you that using the power rule. Okay, so if you've seen calculus before and you're like, obviously, Judy, x squared has a derivative of 2x because we just used the power rule, you would be correct. but this is why we end up with the 2x. We pick a point, 2 points that are super close together. We try and find the slope that describes that tangent line. Turns out 2x will help us describe that slope. We'll get more into the idea of like what's a derivative, but the biggest takeaway from this second part of class is a lot of this algebra stuff, okay? I see a question in the chat. What is the simple definition of a derivative? Are you referring to the formal definition? Yeah, I don't know that there's a simple definition, but we will start to talk about that more on Wednesday. Okay, we'll talk a little bit.
Wasn't necessarily like just like what's the purpose of the derivative, but I guess it's just the IROC, which is the instant. Like, okay.
It is, and let's think about this. What we're really saying is now we can describe the slope of a function, right? And it doesn't even matter what the function looks like. The slope could be different everywhere, and we could still describe the slope. And that's sort of the purpose behind that, okay? All right. So let's, I'm gonna ignore this question. We'll come back to that again later. But because of the time that we have, I'd like to spend it more on figuring out, like practicing some of these algebra steps, okay? So let's take a look at example 2, right? It says, find the derivative for the function f of x equals x squared minus 2x using the formal definition of the derivative. Okay. So like before, I'm going to go ahead and write down that formal definition. I'm going to say that f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And we're going to call this f of x, the green one, just like we did last time. And we'll call this f of x plus h, the purple one, like we did last time. Okay. Now, I do want to go back and maybe use the space above to say f of the input. Could someone describe to me what I would write over here for this function? Because now this function is a little bit different.
You would write negative x squared plus 2x.
Where'd you get negative x squared from?
So because we're subtracting, well, that's technically a negative applies to the whole f of x equation. Wouldn't you then distribute the negative to the entire input, the entire f of x input?
Oh, this is the whole function, x squared minus 2x. So I think I'm not asking the question well. What I was asking is more like something like this, right? Like if you have f of x equals x cubed, how do we write it with the word input? Right? Or if I had x squared minus 2, how do we write that with the word input? Or if we had like a different function, how would we write that with the word input? Okay. So if we think about that down here, all right, so maybe it's sort of like ignore this part for a second, but just think about this function. If we were to replace all of the x's with this word input, we would get something like input squared minus 2 times the input. Does that make more sense? What I was asking for?
Yeah, that makes a lot more sense.
Okay. All right. So let's say we wanted to find our f of x plus h for this function. What would we write for f of x plus h?
X squared minus 2x plus h.
So x plus h squared minus 2 times x plus h. Exactly. And this, my friends, this whole thing is f of x plus h. Okay. So let's go ahead and substitute that in. So I've got the limit as h approaches 0. It's going to get real long. And I've got x plus h squared minus 2 times x plus h, right? So all of this is the f of x plus h. That's the point that's really close to the one we want. Minus, what do I put in for the green part, the f of x?
But the function actually is just x squared minus 2x.
Great. All right, so all of this comes from our f of x. And on the bottom, I keep the h, okay? Great. Let's make things even messier. Okay, this is going to be a theme for us this semester. We're going to make things messier before we make things better. Boom. Limit as h approaches 0. A long fraction line because it's going to get messy. X plus h squared is going to give us x squared plus 2xh plus h squared. What do we get for this second clump in the purple?
Wait, really quick, wouldn't it be a positive 2x because the negative distributes?
Okay, I'm gonna get to that in 1 second. So let's do this purple part first, and then we'll talk about that green part, okay?
Back to the purple part, it would be negative 2x minus 2h.
Great, so all of this is the purple part, right? Now, I'm so glad that not just one of you, but at least 2 of you are sitting here thinking, Judy's got a big old mistake on the screen, because I do right now. I want to subtract all of the green. So I either do what Dallas said and put parentheses around that, okay? Or I make sure that I distribute that minus sign, right? So in both cases, it would be minus x squared plus 2x, right? This minus sign gets distributed. That's how come we get the plus there, right? I intentionally left that off because it's so easy when we're working to be like, we just keep writing, and then we just forget about the parentheses. And what happens is when we forget the parentheses, sometimes things don't cancel out anymore. And remember how I said there was sort of a clue that at some point, all terms should have an H? If you feel like you're not getting to this point where all the terms have an H, I bet there was a sign mistake somewhere. And it's the smallest mistake, and it brings us so much frustration when we miss it, right? But it's a really good reminder. Be patient with yourself. If you don't get to this stage where all the terms have an H, maybe just go on back and just make sure you distributed all the signs you were supposed to, okay? So let's see what cancels out. I notice that this x squared and a negative x squared, those go to 0. I notice that this negative 2x and the positive 2x go to 0. What do we have left? 2xh plus h squared minus 2h all over h. Let's do a quick visual check. Does every single term have an h? Yeah, every single term has an h. That's great. Factor that h out, reduce, and now we get to plug in 0 again and see what happens. And so when we plug 0 in this time, no problems. We get 2x minus 2. Okay. And so if we were to sort of summarize in words what this is saying, this says that the derivative of x squared minus 2x is 2x minus 2. Okay. Now I noticed earlier that I think Alexis, you asked a question, isn't there another formula to solve these with the ddx formula? Yes, there is. And that's what we're going to do sort of after the break. So, or not the break, but after in exam 2, that's really what we're going to focus on, is all the rules to do this in sort of a shorter way. All right. But a lot of these algebra skills that we practice here, even if we don't use these to find derivatives, all of these algebra skills that we're building are really going to help us with the rest of the content. Okay, so maybe there's a faster way to find a derivative, but maybe also we need to practice those algebra skills. Okay, for those of you who are going to be continuing on to Calc 2, Calc 2 is super algebra heavy, like way more than Calc 1. And that's where it can be really hard for students. It's like the last math class you might need to take, and it's just, there's so much algebra. Okay, and so I'm trying to build in a lot of it and be really intentional about it. So we're not just preparing ourselves for this class, but really also to be successful in those future classes. Okay. All right, so done 2 examples, both with like a quadratic situation, but there are, of course, other ways to think about like different functions. And we're going to get a chance to sort of review what some of those are, thinking about what we learned about limits last week. Okay, so some of the skills we learned for limits are actually going to be helpful for us when we're looking at this formal definition as well. So let's take a look at example 3. It says find the derivative for the function f of x equals the square root of x using the formal definition. Now, I know that it's can be hard for me to remember formulas, right? I'm not the best memorizer. Some of you out in this class are way better memorizers than I am. But some of you might be more like me, where it's like, oh, I think it was like this was the formula, but I can't really remember. Every time I do these problems, even when I'm teaching, even when I'm not teaching, I write out the formula because it helps me remember it. Okay. The more times I write this formula, the more likely I am to remember the formula when I get to an exam. Okay. Oops. All right. Can someone tell me what the f of x plus h is going to be in this case for this particular function? All right, we've got one one guess out there, one conjecture, the square root of the whole thing, x plus h. How do we feel about that, class? Agree? Do we disagree? Mhm. All right. So let's think about that word input, right? Everywhere we see the X, we're going to replace it with the word input. The whole input goes inside that square root. Then I have my f of x. All right. So here's my f of x plus h. Here's my f of x. All right. Now, I did kind of say, hey, we're going to use some skills from last week, or actually 2 weeks ago. How might we handle this?
Conjugate.
Yeah. We see the square roots. We think, oh, we've seen this pattern somewhere else in a different context. But let's try using it here. Okay, so square root of x plus h minus square root of x over h. What is going to be my fancy way of saying 1?
Square root of x plus h plus square root of x.
Nice. We're going to keep the same terms, but we swap the sign in between them to be different than it was before. And because we don't want to change the problem, we have to do that on the top and the bottom. Okay. Which part of the fraction should we simplify, and which part of the fraction should we be patient with?
Multiply the top, leave alone the bottom.
Yeah, so we're going to multiply the numerator and keep denominator as is. Okay. How do we know that? Sort of as a nice review from last week, the numerator is where the conjugates are. So that's why we're going to multiply them out. We hope that it cancels with something that we were patient with on the bottom. I will leave this rest of this problem as an exercise for you to finish. All right. I think we're all in different places with our algebra. But at the end of the day, we should end up with this. Okay, so we'll skip a few steps and I'll leave you to check that final answer. And if that's something you want to work out and send me a picture of your work on Discord, I'm happy to check it over. Or if you want to come in on Wednesday morning and take a look at this, like I tried to get to this answer, I'm not sure that I did it right, or you just want to check it over, we can go over that during office hours. I'm sure if you ask Ethan to walk through the rest of these steps with you, you can do it in sort of a collaborative way, right? So good chance to kind of practice where we individuals might need to practice. Okay. All right, got just enough time to look over and set up the last 2 questions that we have here, okay? And let's take a look at those 2. All right, so we have find the derivative for the function f of x equals 9 over x using the formal definition of the derivative. So I'm going to set things up. I want to write my f prime of x equals the limit as h approaches 0 of my f of x plus h minus f of x all over h. Can someone tell me what they think our f of x plus h is in this case? Right, so what are we going to put in for the purple? All right, I see Dallas has put in a conjecture in there, 9 over x plus h. And I'm wondering if someone can take that and maybe make it a little bit more precise. Mm, 9 over x plus 9 over h. These are all great guesses. Right? Maybe we take a moment and write this as f of input equals 9 over input. Okay, so we've got 3 options so far. 9 over x plus h, 9 over x plus 9 over h, or 9 over the quantity x plus h. All right, so let's call the first one A, the second one B, the third one C. Which of those do we think matches best with this structure? Yeah, yeah. Right? If this helps you, write it out, right? Like, don't be ashamed to like write it out with the word input and then be like, oh, now it makes sense to me, right? I would rather you write this out than like try and figure it out in your head and get it wrong by accident. Like that would actually make me really sad, right? So 9 over input it is, so we would get 9 over x plus h, right? Minus 9 over x. And this would be my f of x plus h. And this would be my f of x. All right. Now, what strategy from last week or the week before do we think would be helpful here?
Complex fractions.
Yeah. Complex fractions. All right. So I'll leave that to you. I think it's a great chance to practice complex fraction on your own time without being pressured to think fast through it or, have people like sort of coach you through the questions. I think this is actually a really good way to prepare for that exam next week. Can you do this? Right? And if you can't, you've got plenty of time between now and next Wednesday to come into office hours, come to tutoring, post it on Discord, whatever suits your fancy to make sure that it's something that you get before you walk in the door. Okay. But the end goal should be -9 over x squared. Okay. All right, let's do one more where we're setting things up. All right, so example 5, find the derivative for the function f of x equals 1 over the square root of x using the formal definition of the derivative. All right, formal definition, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, we know our f of x, and we have to find our f of x plus h. All right, what are our guesses for our f of x plus h? What might that thing in the purple look like? Yeah. All right. I like this. I like this. Right? We're getting better each time we write something. We're modifying things to be more precise. And in fact, in this one, it is 1 over the square root of x plus h. Right? Minus 1 over the square root of x. Now this one, all right, so let's say that you're sitting here and you're like, Judy, examples 3 and 4 are pretty easy for me. I don't really want to go and do that on my own time. Example 5 might be where you're like, this is where I would like to put in my practice time. That we're using complex fractions and conjugates together. Right? So lots of different levels for us to kind of try and practice where we need to practice. Or you could be like, no, Judy, I want to be extra prepared. I'm going to do all 3 of these examples, and that's also great, right? But at the end, your goal answer is -1 over 2 times the square root of x cubed. Any one of these questions, and example 3 on the previous page, any one of these is fair game to be like, I have questions on this. Can we do a few steps together? That's absolutely fine, okay? If you're looking at these and you're like, there's no way I could do these by my own and she's not doing them in the lecture, we can work on them together during office hours, or you can just send me some messages on Discord and be like, is this a good first step? Is this a good second step? Okay. So when I don't do the full example in class, I'm not saying, oh, this is so easy, you should be able to do it on your own. It's more just like, let's build in that practice. Let's get a good indicator of where we are before we walk into that exam next week. Okay. The very last thing that I want to leave us with today, this is another example you can use to practice later, okay, is this last question. Someone sort of mentioned this notation earlier. I think, Alexis, it was you. Something about this dy dx, all right? So anyone who's taken calculus before will just sort of plant a seed that f prime of x is the same thing as saying dy dx. Okay, so I've changed one small piece, but I've kept the rest of the question the same just to get us used to maybe there's another notation we can use to solve this. Okay. This is a great practice problem if you're like, I didn't really understand the first 2 that we did together. This would be a great one to start with. Okay. All right. So we are right at noon, which is great because that is when class ends. I don't want to keep you any longer. I want to respect your time.